Good morning, good afternoon, and good evening, and welcome to Connecting U's exclusive webinar series, What is MIMO? My name is Brad Schubert, and I'm a multimedia instructional designer here with Cambium Networks and the author of Connecting U. With me today is Mark Hemmon, who is the newest member of Cambium's training team from the acquisition of Xeris. Mark, would you like to tell us a little bit more about yourself?
Yes, thank you, Brad. Again, my name is Mark Heeman, and I came to Cambium with the acquisition of Xeris. I've been with Xeris a little over 7 years now. I'm quite familiar with the Xeris products, and I'm quite familiar with the world of Wi-Fi. So I'm hoping that I can lend some expertise to this conversation.
Thanks, Mark, and welcome to the team. Let's get started with the obvious question. What does MIMO stand for?
Very easy. Multiple input, multiple output.
Can you briefly explain what MIMO is?
Sure. So MIMO technology was introduced in 2009 as part of the 802.11n specification. It's one of the primary technologies that allowed Wi-Fi speeds to jump from 54 megabits per second to 450 megabits per second. And here's a quick high-level overview of MIMO. In its simplest form, MIMO is an antenna technology for wireless communications that allows multiple antennas to be used at the same time when sending and receiving data. This represented a big change in the way antennas had previously been used in Wi-Fi communications. To understand this better, let's go back several years before MIMO came out. Wireless devices will have had either one or two antennas, and even though a device had two antennas, before MIMO was introduced, only one antenna at a time could be used. A laptop is a great example of a wireless device that has two antennas. The antennas typically run up and down the sides of the screen. When the laptop started to communicate with another wireless device, the laptop would figure out which antenna is providing a better signal strength and then use that antenna for the rest of the conversation with that other wireless device. This is known as switched diversity. Using radios and antennas like this is known as SISO, single in, single out. The problem the legacy wireless networks and wireless devices had to contend with is a phenomenon called multipath. Let's remember, in its most simple form, Wi-Fi is all about manipulating airwaves. A transmitter sends out airwaves, and a receiver receives these airwaves. When a transmitting radio sends out airwaves, everything and anything the airwaves come in contact with, including open air, will affect the airwaves in a negative way. Airwaves can be reflected, scattered, diffracted, or refracted. This causes the original signal path to be split into multiple paths of that same signal. And oftentimes what would happen is these multiple paths will hit the receiving radio antenna at different times, nanoseconds apart. And this could cause loss of signal strength and data and corruption. I only bring this up because MIMO turns multipath from a bad thing into a very good thing. And we'll talk about this later. So sorry about the history lesson. Let's get back to MIMO. MIMO technology provides a way for a transmitting radio to split a signal data stream into data streams and send these multiple data streams simultaneously to the receiving radio. The receiving radio will use its multiple antennas to receive the separate data streams and then reconstruct them into a single data stream. Using MIMO technology and multiple data streams, the result is a stronger signal to the receiving radio. And when combined with the technique called spatial multiplexing, bandwidth speeds could now be doubled or tripled and sometimes quadrupled. The 802.11n spec called for up to 4 simultaneous streams, which would effectively quadruple the speed. But the reality is that the industry never developed a 4-antenna 802.11n radio. 802.11ac spec was coming out soon, and everyone stopped development on the 802.11n radios and shifted over to the 11ac radios. Back to multipath. In a typical indoor environment, multiple RF signals sent by a MIMO radio will take multiple paths to reach the MIMO receivers. We'll then sort out the multiple signals and reconstruct them. So actually, a high multipath environment helps a MIMO receiver differentiate between the unique data streams carried on the So actually, a high multipath environment helps a MIMO receiver differentiate between the unique data streams carried on the multiple RF signals.
So what are some of the basic concepts in MIMO technologies?
MIMO systems will use multiple antennas to provide for better transmit and receive diversity. A RF signal may be affected by any number of environmental factors, resulting in fading of the signal. This will impact the received signal strength and signal-to-noise ratio. In turn, this will cause a rise in the error rate, which we need to avoid. One of the primary components of MIMO is diversity. The principle of diversity is to provide the receiver with multiple versions of the same signal. Diversity helps to increase the reliability of a link and improves performance. This will increase the range of the radios and reduce error rates. Several different diversity modes and techniques are available and provide a number of advantages. The first, which I've already mentioned, is spatial multiplexing. Spatial multiplexing provides for greater throughput and takes advantage of our old nemesis, multipath. Space-time block coding and cyclic shift diversity are a couple of transmit diversity techniques where the same transmit data is sent out on multiple antennas. Using time diversity, a message may be transmitted at different times. In other words, using different time slots and channel coding. This allows the stream to take a different data path, which, when received and recombined at the receiver, will produce a stronger signal with a higher signal-to-noise ratio. Space diversity, used in the broadest sense of the definition, is used as the basis for MIMO. It uses antennas located in different positions to take advantage of the different radio paths that exist in a typical terrestrial environment. Forming is a technique where the same signal is transmitted over multiple antennas and the antennas act like a phased array. Having multiple data paths is really helpful because if the signals are using different signal paths, the probability that they will all be affected at the same time is considerably reduced. So MIMO utilizes a receive diversity technique called maximal ratio combining. This is where the multiple received signals are combined, thus improving the overall signal strength and improving the signal-to-noise ratio.
You mentioned that MIMO systems will use multiple antennas to provide for better transmit and receive diversity. Can you talk a little bit more about that?
So let me start with radios and radio chains. This is an important concept in MIMO. As I've already mentioned, legacy 802.11 radios transmit and receive RF signals using a single antenna. This is known as SISO, single in, single out. SISO systems use a single radio chain. A radio chain is defined as a single radio and all of its supporting components, mixers, amplifiers, and analog to digital converters. A MIMO system consists of multiple radio chains, with each radio chain having its own antenna. So a MIMO system is characterized by the number of transmitters and receivers used by the same multiple system is characterized by the number of transmitters and receivers used by the multiple radio chains and also the maximum number of unique data streams supported by that radio. When referring to a MIMO system, you will typically state a series of three numbers. The first number will indicate the number of transmitters. The number indicates the number of receivers. The third number indicates the maximum number of unique data streams the radio can support. For example, a 2x3x2 radio system would consist of 3 radio chains with 2 transmitters and 3 receivers and supporting a maximum of 2 unique data streams. A 3 system would use 3 radio chains with 3 transmitters and 3 receivers and supporting a maximum of 3 unique data streams. A 3x2 system would use 3 radio chains with 3 transmitters and 3 receivers and supports a maximum of 2 unique data streams. So the number of simultaneous data streams is limited by the minimum number of antennas in use on sides of the link. So for instance, if both the sending radio and the receiving radio have 3 antennas and each radio supports 3 unique data streams, then it would be possible to have the data streamed across all 3 antennas. If the sending radio has 3 antennas and the receiving radio has 2 antennas, then the best possible number of simultaneous data streams would be 2, which matches the number of antennas on the receiving radio. Of transmit diversity is called space-time block coding. The technique of transmit diversity is called space-time block coding. The same information is transmitted on 2 or 3 antennas. This is used where the number of radio chains is greater than the number of spatial streams. The 3x3x2 radio is a good example of this. This technique will not necessarily increase the throughput, but what it will do is increase the receiver's ability to detect signals in a lower signal-to-noise ratio environment. Here's a little food for thought. If you cover one of your ears with your hand, will you hear better or worse? More than likely, you will lose some hearing capabilities if you cover one ear and now only hear out of one ear. Taking this idea a step further, do you think you would hear better if you had 3 or 4 ears? You might look a little silly, but you would definitely be able to hear better. MIMO is very much like this. The use of 4 antennas is much better than 1 antenna. Diversity, both transmit and receive, is a method of using multiple antennas to survive the negative effects of multipath. As the distance between a transmitter and receiver increases, the received signal strength decreases and gets closer to the noise floor. So your signal-to-noise ratio drops, and bad things like a dropped signal or increased data rates will start to occur. Which diversity system, I mentioned this earlier, listening with 2 antennas increases the odds of hearing at least one signal without corrupted data, and your odds get better with 3 or 4 antennas. When received diversity is used, the signals will be combined, allowing for a better estimate of the original signal. This effectively produces a stronger received signal with an increased signal-to-noise ratio.
Earlier, you mentioned spatial multiplexing and its benefits by increasing throughput. What is spatial multiplexing?
So we've talked about MIMO radios and how they will transmit multiple signals at the same time. MIMO radio also has the capability to send independent, unique data streams. Independent data stream is also known as a spatial stream. And here's the great part. Each unique spatial stream can contain data that is different from all the other streams transmitted by a different radio chain. What we're doing is splitting a signal into multiple parts and then sending each new part through a separate radio chain. So now the signal goes out in 2 or 3 or 4 parts instead of 1. To this goodness, each spatial stream will take a different data path because there's a very slight time difference between the transmitting antennas. The fact that the multiple streams will take different paths due to the timing difference is called spatial diversity. This process is often referred to as spatial multiplexing. The benefit of sending multiple unique data streams is that the throughput is drastically increased. Using 2 spatial streams will effectively double your throughput. Streams will triple your throughput, and using 4 streams will quadruple your throughput.
So how did MIMO evolve into the technology that it is today?
Well, MIMO technology has been developed over many years. Not only did the basic MIMO concepts need to be formulated, but in addition to this, new technologies needed to be developed to enable MIMO to be fully implemented. New levels of processing were needed to allow some of the features of spatial multiplexing, as well as to utilize some of the gains of spatial diversity. Up until the 1990s, spatial diversity was often limited to systems that switched between two antennas or combined the signals to provide the best signal. Various forms of beam switching were implemented, but in view of the levels of processing involved and the degrees of processing available, the systems were generally relatively limited. However, with the additional levels of processing power that started to become available, it was possible to utilize both spatial diversity and full spatial multiplexing. The initial work on MIMO systems focused on basic spatial diversity. Here, the MIMO system was used to limit the negative effects caused by multipath propagation. This was only the first step, as the system then started to utilize the multipath propagation to its advantage, resulting in a stronger signal strength and reduced signal-to-noise ratios. Another benefit is that by splitting the data stream and sending each part through a different antenna, this allowed the throughput to be doubled, tripled, or even quadrupled.
Thanks everyone for your time today, and look forward for more Connecting You exclusive webinars like this one coming soon.